Hear me now. I can hear me now. So, any of y'all come from the Open Hardware group? We call them, okay. Anyone wanted to see a talk on Internet of Things devices when we said embedded? Okay, you lose. We're not going to do it. We'll just touch on it. So, let's start out. When I say embedded, what do I mean? It's a component of some device. Your software runs on hardware that's built into something else. So you got very little power. You got very little memory. I mean, I'm running huge embedded devices for this stuff, and they have a whole half a meg of memory, maybe a meg, right, for the big ones. And your peripherals are limited. You get LEDs and maybe push buttons, and if you're really lucky, motors and servos and stuff like that, or an LCD. No OS. That to me is the critical application. You run on the bare metal. You talk directly to the hardware. You grab memory and poke bits into it, and it makes things happen in the real world. And likewise, when you get an interrupt, your code handles it. There's not an operating system in the middle. You may have heard of the Raspberry Pi, which is a small Linux board that people use for embedded systems, but well, it's a Linux board. You get to talk to the you have to get the operating system to let you talk to I/O devices, and it does all of the hard work. I don't think it's nearly as much fun. So now Python in this environment. Let's look at the things that make Python nice. It runs in a VM. So it's constrained. When it crashes, you get an exception trace back, and you're back in your REPL. And you don't go out and do things like, well, actually, one of my bosses had a job. He said, when I get a bug on this job, we get 3 feet of concrete, right? Bugs in the REPL aren't quite that nasty. You don't get wild things. You get garbage collection. You don't have to worry about your memories. And you get the REPL, which is a wonderful place to product things. On the other hand, when you look at things that make it slow, well, it runs on a VM, it does garbage collection, and you get dynamic typing. So maybe not the best thing in the world for embedded systems. µPython was designed for embedded systems. The original is a thing called the Breadboard, which mine's still in shipping. Right, didn't bring one. But there are builds available for other platforms. I've got 4 of them here, and we're giving away one. All right, most of them are STM micro devices, Cortex M4 boards, the STM32F4 invariants, and that's what I've got here. Adafruit makes hardware for the maker market, basically. They build embedded systems, the Arduino stuff, lots of things. They have a variant for their boards, and that's a lot of Internet of Things type stuff. And their claim is it's easier to use. And there is the BBC Microbit, which was designed for the educational market. That's the funny little white thing over here. It's actually a small board about 1 inch square. And they have a version for that. It runs on lots of interesting hardware, though none of the really small stuff. Yeah, here's the list of ports. The STM32, lots of support, lots of options. Internet of Things devices, the ESP8266 hardware, and the CC3200, both of which do Wi-Fi. You can run the Python web app, web server and clients on it. Talk to your REPL via the web. Getting to the REPL on these devices is always interesting. There are desktop variants. It will run on Unix, Windows, and in an emulator. And there's a few other devices. There's an RTOS minimal build. A Teensy is an Arduino type STM device. And at this point, you want to see the robot run, you want to look at the code. Anybody care? Yeah. Which one? Okay, let's see if it works. Hey, it's a build in progress. Always a question. Phone. Now, all of the code running on the firmware is written in Python. Well, all of my code's written in Python. And connect. Second light went on. We are connected. And, oh. The board I'm using came with a beeper. I connected it. Lights. I mean, it's just, it is little more than an RC toy at this point. But like I said, the interesting part is that all the code is written in Python. All the code I'm using. Yeah, actually I can. Let's see, did I leave that? Yeah. Excuse me, I've got the, not running my normal. Come on up, there we go. Controller. And we connect it to, oopsie daisy. Oh, forgot something. What? Hey, I'm going to write it in Python. What can I say? I have, let's see. Okay, let us lose that one for now. I meant to bring a USB hub because all of my devices are. So let's try again. Where is? This time, please. There we go. No, USB Bluetooth dongle on the laptop, right? I didn't have it in. It lost the binding for some reason. I had to go rebind it. But I can see it from here. You see there's two green lights on the back. One of those is the system is up and running. It's not just power. It's I booted, I loaded up all the tank software, we're ready to go. The second one is we're connected. And I can test it. Yeah, we're connected. Turn on the lights. This is just differential drive XY control, right? Push it forward, it goes forward. All right. Nothing really fancy here. I like differential drives. Now, you know, future plans, I've got ultrasonic sensors to add to it. I don't know if you heard, this is sort of on short notice. Extra devices, I looked at adding gripper claws and the like. That's a carrying platform for me to play with robotic stuff. The fact that it looks like a tank, well, it was inexpensive and tanks are cool. All right? So now can we go look at the, would you like to look at the code? Yeah. Okay, oops, let's see, Control B. Go away, oh well. Okay, now I have this card over here. I copied the code from that system, which, just to show you, this is the F411RE. That's the hardware that's inside of this. That's what they're giving away over here. So I hope you're all signed up. Okay. The flash memory has its own file system. That's where my Python code is stored. It exports that via USB. I can mount it. So if we just look around in here, here we go. Boot.py is a Python script that's run when the hardware boots. All right? I use it for defining things that I like to have available in my REPL. You can use it for setting up hardware, initializing stuff that needs to be dealt with on power on. Oops. Oh, I do not have a main.py. Why don't I have a main.py? Okay, I want to start with that. We're going to, The light went on back there again. I'm now talking to the REPL running on the tank because I wanted to look at main.py.
These are always the basic debug tools you write first when you get into a new environment.
Yeah, well, if you look at the boot.py here, I spent a lot of time in the REPL on this, so you'll see there's, from UOS, cd, ls, get pwd, rm, mv, a cat command, and there is a Unix ed clone written in Python that's actually in the flash. So, main.py. There's a little bit of stuff we want to shut down a motor driver that's not in it anymore because when it came on and turned it on for me, but you can't see my hands. So we import the tank object, then we import some motors. Come on. Build a tank, it'll do it. And that stuff, like I said, not there anymore. And basically the rest of it is we add devices to the tank. And then we turn on, pin refers to a hardware pin on the device. If you're programming, this uses Arduino pin names because they're available here. And A4 is the second light. So the last thing it does is turn on the A4 light to let me know that the tank is ready to connect to it. Right? Nothing fancy there. Now we're going to go back to the easier one. Okay, now we're looking at this code again. We can look at tank here. From PYB is the Pi board. That's where your hardware lives. We want pin, and we're going to have an ADC. Oh, I didn't show you that. Oh, well. Tank. It has lights, a battery. It's a cannon. Not there yet, but which aren't there. The ready, which we can call, ready is the last thing we called. We just pass it a pin. It says, okay, make sure the pin is an output pin, turn it on. That's all it does. That's how you turn on a light. We have a battery that uses, again, everything happens through pins, or almost everything. And we save the pin and divider because the pin only handles a range from 0 to 3.3 volts. If you try feeding it more than that, you will fry your device. And you don't want to do that. And then to get the value, it goes out and reads way over here. Reads the ADC, multiplies it by 3.3, the maximum readage, multiplies it by divider, divides it by the 4096, the resolution, right? So this shows you the battery. Let's go back and look at that. I have that. If we fire this up again, did I leave that connected? No, good. When we connect here, I meant to point that out at the time. Way down here it says battery not connected, battery 8261, all right? Current voltage, because, well, if the battery runs out, it won't come home. I don't like to walk to pick it up. I also fly aircraft, and when the battery runs out and you walk to pick those up, you pick up pieces. So we don't do that. Let's go back. I mean, that's pretty much what the tank device is. We connect pins to it, and we have devices. This is in a state, and we have commands that go out and toggle the pins. You know, we can add lights. It keeps an array of all the lights on the device, and we call that and pass it a value to turn on and off. Horn, separate controls for the lights up here. Horn, adding motors, can add a motor, save it, and when we add the motor, we set it to off or coast, and then we just pass the speed on down to the motor device when it comes in. Go forward, backwards, brake, all right? Fairly simple. Y'all notice what's missing here? Did you see any way to talk to the tank? Yeah. Well, You can see, stop that. If we go out and connect via the, I can turn on the lights. Don't want to run them, talking to the REPL, I can reach the tank, toggle the lights. Let's see. Oh. We'll run it forward a little bit. Okay, so this is, go forward at full speed. 0 to 100 is full speed, minus 100 go backwards. Delay for half a second, and then hit the brakes. Right? Just at the REPL. So that is actually the comm system here. If come on, there we go. If I fire up TK enter again, connect, and, oh, where is it? We can, okay. We can switch to the other side, T-dot horn. Oh, let's turn off the lights. There we go. It just, turn off the lights, switch back. If I run this out, my switch button, you can see the commands that it sent just bouncing off the REPL. That is the comms for this. It just, the application program, both this and on the phone, just talk directly to the REPL and reference the device, send it commands. I think that's cool, right? I can't do that in C. It doesn't have a REPL. I can't do it in, you know, whatever I might want to be using here. So that's the demo. Where am I? Just to show you a little bit, oh, I know, there we go. You've seen turning stuff off and on more. This is not on the tank. This is the Ultrasonic Ranger rangefinder. A little bit more complicated here because the way this works is we have 2 pins. One is a trigger. We drop the pin, raise it for 10 microseconds, and drop it again. That sends out an ultrasonic pulse. And we have set things up here. This line and the one below it catch the return pin and attach an interrupt to it. When we get an interrupt, it's going to call, where is it? Yeah, self.IRQ, my non-maskable interrupt. Down here we see IRQ, we check the value of the pin. If it just went high, then the pulse is coming back. We want to watch for it. If it went low, then we can save our elapsed time. That's how long it was. And up above that, you can see we have SOS, the default, is the speed of sound. We just take the elapsed time, multiply by the speed of sound, divide by 2 because it goes out and comes back. All right? But this is what embedded programming is like. Is you wrap hardware and it does things, and then it pokes you back to make you fix it. Now Python, µPython in particular, is really nice for this because, as you saw, I can connect to a REPL on my tank, on this board, and just change stuff. Poke it, toggle a bit, make sure I've got the right one, see if it works, test it. I can run, just like writing Python or anything else, right? If you're used to using a REPL. Let's see what else I had here. And I think we just went through, yeah, I got the demo, lights, buzzer, voltage telemetry. We don't have the range sensor. Tank, didn't show you the motors. Lights and buzzer, they're pins. You turn them on and off. Pulsing, we did that. So yeah, this, to me, this is sort of like a software breadboard. When you're building hardware like this, you start with a breadboard. So you can just plug, you can just plug wires into it without soldering anything, connect everything up, make sure it works, test it. Python is the software half of the breadboard. It's fast to plug stuff together, test it, see if it works. When I want to go back and actually build what's going to go into production, I will pull apart the breadboard, solder parts to it so they don't fall apart. I may well decide, okay, we don't want to use Python for this. That's a relatively expensive board. I mean, these boards, they're $10 to $15 a piece, but still, I can buy a Arduino that might be able to do the job for $1.50, right? But, you know, I've worked out what everything needs to do and how it works. I can translate it to C and compile it for the Arduino. Don't need a REPL. Basically, it's the equivalent of soldering it. It's much harder to change. It's harder to put together, harder to change afterwards, but it uses a lot less resources. We didn't look at our shell. You saw I was looking at the files on the flash drive. I can edit them, save them. I hit Control-D, and it will reload my main file, restart it to make changes on the fly and test it. I mean, this is Python 3. They don't really like you to re-import modules. Yeah, this is actually Python 3.4 something based on. It is fairly complete. Boot, post one. Once I've got stuff working properly, or mostly properly, I mentioned that ED clone. You can take your Python file and compile it and flash it into it. You can't look at the source, right? That's actually what a lot of the code running on this is on the tank. And like I said, I brought some boards here. This is my favorite dev board. This is an STM32F4 Discovery, and they've been discontinued, right? They now use an STM32F411 Discovery, which has half the memory. I don't have one, can't recommend it. You showed you the F411. That's nice because it uses Arduino headers. That's a standard that's really popular with people who like building their own hardware. What you're looking at, if you look down into the tank, and please feel free to do so, is a shield. It plugs directly into the Arduino headers, gives me pre-assigned pins for everything. That's what actually talks to the motors. And the reason this thing has a horn is because the shield came with a beeper, and I figured I've got it, might as well do something with it. It's got connectors for everything else. You can buy LCDs, SD cards, lots of stuff that's relatively inexpensive because the Arduino is so popular. This is another Discovery card, built-in LCD. Don't like it for development because the LCD uses a lot of my I/O pins. And it doesn't have any real advantage over that except the LCD. This one's hard to see. This is actually a BBC microbit with a small robot built attached to it. There is the front card here, right? That and below is the actual microbit, a couple of square inches, LED array, button, designed for the educational market, runs µPython. The problem is the Bluetooth stack and µPython don't both fit in memory at the same time. So if I want to use it as a remote control robot, I can't do it in Python. Got a little shield servo with motors, kind of cute. More expensive. I brought some miscellaneous hardware. That's what the ultrasonic sensor looks like. That's going to attach to the front of the tank at some point. This is the STM32 Blackboard. It's open source hardware design. Same processor as the Discovery, right? But no LEDs, nothing but a button and one LED. This is sort of a canonical development system. You get one button, you get an LED, you load it up, make sure it blinks and works, and then you go back and solder everything to it. I put headers on, I was going to play with it as a dev board. All of these boards are about $10 to $15, except the microbit. That one's a little bit more expensive. And they're from the manufacturer. Let's see, do we have a, yeah, you got links. From the manufacturer or someone. They are not, well, this one is a Chinese copy, right? Made in China, got to wait for 3 weeks for it to show up, but it's an open source hardware design. You get lots of stuff that way. The rest of it is from the original manufacturer, ST Micro, nice and inexpensive hardware. and really powerful for what you get. Hardware in the tank, I mentioned that. The Nucleo F411RE, a 0.5 mega flash, 192K of RAM, and that's about it, right? Button and LED, that's what you get on the thing. There's a Fundamoto Arduino shield. It's got a couple of motor drivers, the horn, and connectors for lots of stuff. There's an ACO5, go back, ACO5, if you look at the back near the lights, you can see the little stick coming out. That's my Bluetooth serial module. And yesterday, I finally got things to the point where it's going to move inside underneath the turret onto the Fundamoto shield. Issue with the Nucleo uses the serial port on the Nucleo hardware is used for things other than, well, the serial port that the Fundamoto shield connects its Bluetooth connector to is used for other things on the Nucleo. I had to sort out how to get that off, how to undo that. But it's going to move inside. We'll add some buttons and stuff. The chassis is an SM100 chassis from Cinnamon. It happened to be on sale when I went looking. The cover on top has the lights. The turret is not here. And it's not here because I was expecting a servo to control the turret, and it showed up with a motor, and I don't have another motor driver in the thing. The ultrasonic rangefinder and the motor shield is not there. It's going to drive the turret. And that actually is pretty much everything I wanted to show you at this time. Anyone have any questions about it? I know I went through it really fast.
The virtual serial connection across Bluetooth, is that reliable?
Actually, it's fairly reliable.
Is it error corrected?
No, there is no error correction. That's actually one of the things that I wanted to do with this. The Bluetooth stuff is to get the robot control software working. The next step is going to be to put in an RF module and write a protocol for robotics control for that, right? That will do, well, actually you don't want to do error correction on this, because if you're sending packets you're sending 50 to 100 packets a second, you don't want to stop and wait because the packet was bad. You just send the data again, right? And well, that's a whole other talk about the protocol. Anyone else?
How much free space do you have after you load your module?
Let's go look. I believe it will tell me. You know what? I'm not. Yeah. Oh, I'm sorry. You can see I've got. Yeah, it's all in hex, right? I don't. I want to be too lazy and do it, but you can tell I'm using. RAM starts at 2 million here, runs out to 200,000. I'm using, the heap is using, I guess lots of it. I've got about a sixth of it, let's see, trying to do this in my head. Looks like about a sixth of that is being used for my static variables. The heap is using about twice that. And there's a little bit more than that that's free. So not a lot of RAM. Flash data. Yeah, flash data, on the other hand, I'm using about a quarter of what's available. All right. So we're fine for flash. RAM, might want to watch out for. And you can tell the garbage collection times and totals. 37,000 free bytes free last time it did a garbage collection. Anything else?
Is there any utility or tool that you wish you had that just won't fit? Anything you're missing that you wish you had?
Well, okay, this is about the smallest card that µPython will run on. And if I build the debug version of µPython with symbols in it, it don't fit. That's probably the biggest one, right? It takes a little bit of work to get a version to debug if you're having problems in the Python interpreter itself. I haven't tried to put anything with it, but I'm coming from working in C on really small systems to this. So, I mean, I don't believe, I don't think the PyDebugger is available. I haven't tried. I know, like I said, they ported the web server and such like from Python to it, to the ones with Wi-Fi. That works. You know, the dev board here has actually a full meg of flash and just more memory all around. One of the reasons I like it. No, you know, no, I can't think. Actually, the problems I've been running into have been more dealing with the Android phone and Linux on the laptop. The Bluetooth there is kind of flaky, whereas this, I don't do Bluetooth on this. I do, I open a serial port and talk directly to, using serial, and talk to the Bluetooth module that handles it all for me. So it's actually the other way around. Anything else? Anyone else? And I haven't been repeating the questions, and I apologize. Okay, let me give you the, yeah, I'll just leave it up. Links, the repository for the drivers is the second link. The tank software I hadn't got up yet. The µPython homepage where you can download the software, find forms and all that stuff. Arrow is where I recommend you buy the STM boards if you want them. We talked about that. Flux Workshop is where I got the Fundamento board, and I answered a lot of questions about it. Fundamento. They're good people, and Generic Components is from Pololo. Right? Never needed the camera. No, I'm going to leave that up.